开始。
Dear friends, welcome to our video. In this video, you will explore the impact of COVID-19 spread by social distance using agent-based model with Csys5010 together. We have two members in Group 9, Yifei Wu and me, Weijia Zhang. This exploration will look at 6 areas: background, model description, model demonstration, model analysis and evaluation, and further work. Recently, the World Health Organization has declared an end to the public health emergency of the COVID-19, signaling that one of the deadliest and most economically devastating pandemics in modern history is receding as a disease that it has become a common one. They said that COVID-19 will continue to exist, but will no longer cause waves of hospitalization and infections as it did before, as people around the world has built up an immunity to the virus. But the disease, which has affected people around the world for 3 years, is also a wake-up call. Social distance is a key topic of concern for people during the COVID-19 spread. The use of ABM demonstrates that the overall characteristics of COVID-19 disease spread are not simple a geometric collection of individual infections, but more importantly, a dynamic representation of population infections. We can have a more intuitive presentation of the social dynamic of COVID-19 disease spread. Therefore, we choose NetLogo to assist us in constructing our model. In the simulation, the agents are modeled as people in the COVID-19 environment of social life. This project assumes that each agent state in the ABM is susceptible, latent, infected, recovered, and dead. An agent in the susceptible state is infected with the COVID-19 and has an incubation period during which there is a certain probability of transmission to other agents that come into contact with the disease. After the incubation period and the onset of the COVID-19, the infected agent turns to the recovered state or with a certain probability dies. Agents in the recovered state are protected from infection for a certain period, after which they revert to a susceptible state.
In addition, there are 2 ways for our people to move in the model: random walk and unbiased random walk, which are controlled by a button in the code from Fig 5, which means that in the initial setting, if isolation is not adapted, people's movement will be carried out randomly through unbiased mode in all directions. When social isolation is adapted, people in the model will be biased according to the optimization algorithm, and the movement of people will change from unbiased random walk to random walk. R&D extension, which is well rooted in genetic algorithm, will be used on our model. Now let's go to the core of the model, which is the social distance part. In the model, we set 2 parameters, namely max infection distance and the mean social distance. The principle is to let people choose the grid with the least people in their field to move. These 2 parameters represent the maximum radius of infection and the minimum social distance, where the grid with the fewest people in the field of choice is calculated by the minimum social distance. We can determine the effect of social distancing on people's movement by adjusting the size of these 2 parameters. When there are infected people in the minimum social distance or in the maximum infection distance, then people will be infected and get state transferred, and the color will be changed. Let's set the time for latent after infection and time for infected to recovery. Through the citing of these 2 periods and the addition of people movement model, we can see the impact of COVID-19 spread on people with or without social isolation. Finally, we set a protection mode. such as wearing masks, to compare with our social isolation. By opening and closing buttons, we can see the change of people's movement to stimulate the real situation truly, and then move on to our dimension. Now, let's look at our model. We start with 300 population, then click the social distance button from off to on. We can see and press the setup and the go button. We can see the color of the people change and the state of the people is transferred from one person to another. This is because when we turn on the switch of social distance, people's movement changes from unbiased random walk at the beginning to selective random walk. In addition, when I turn off the social distance and adjust the time of latent time and the recovery time, such as 10 and 3. Then we press setup and go again. The distance is controlled by the mean social distance. That is, people need to judge whether the crowd in the minimum social distance is infected before each move and decide the direction of next move to the fewer people grid. Then we finish this simulation and set the latent time and recovery time to the initial state at 7. To compare other variables, we reduce the specific value of mean social distance to 1 and the max infection distance to 3. Then we set up and press go. The model also prevented the spread of the disease to some extent. Next, we will go back to the original state and keep the social distance but off. And we switch the protection button from off to on. We can see that there is not much change in the diagram on the left, but it has something different on the red graphs, indicating that these factors can be used as a comparison to study the influence on of social distance. It can be simply see that when the population returns to the susceptible state, the recovered population reaches the lowest level. In the analyze and the evaluation section, when the population is set up and the go button is pressed, the people's status in the middle is different from the status of the graph on the right when the simulation ends. In the model, gray is dead state, yellow is latent state, red is infected state, and green is susceptible state with recovered with bronze color. It will take a while for the infected state to return to the latent state, which is our pressed latent time and recovery time. As can be seen from the following 3 graphs, the number of deaths due to the social distancing and protection is relatively small, and people move relatively disparate. Thus, better reducing or preventing the spread of disease without protecting and social distance, the number of deaths and infection can rise and fall over a period. And in these 3 graphs below, when we control social distance and protection, the number of deaths increasing to a certain point and keep the same. This is because when the number of people who are susceptible is equal to the number who recover, it means that the number of people infected has been reduced to almost 0 and no new people can be infected. But in other 2 plots, when the rate of infection is faster than the rate of recovery, It causes susceptible people to shift directly to infection rather than recovery at the point of latent, thus entering a new circle that again and again leads to an upward trend in the total number of infection and deaths. Through the comparison of several aspects, it can be shown that the model has a certain good effects on the transmission of disease.
This model uses a random distribution for the population distribution, and furthermore, more complex population distribution can be constructed. For example, the more densely population places, like a city, the faster the virus will spread than a sparsely populated area. And then, as shown in the diagram on the right, there are many control parameters that can be set in the COVID-19 modeling. What's more, some main routes of transmission of the COVID-19 are still respiratory droplet transmission and contact transmission, with aerosol and fecal oral routes of transmission still to be further defined. We only set contact transmission as our project's routes of transmission. Epidemiologically, logical investigation have shown that cases can mostly be traced to having had close and intimate contact with the confirmed case. This means that we can also set up a greater variety of modes of transmission. Here's a reference. That's all for our presentation. You are very welcome to discuss this project with us. Thanks for listening.